start lecture 14, and the course is corrosion protection methods, and topic will be material aspects for corrosion protection. In fact, we have talked about the material tetrahedron related situation, and we could see that processing, composition, microstructure as well as property and finally performance, those are all interlinked. And here performance means corrosion protection and durability, and the property is basically electrochemical behavior, which is nothing but the corrosion behavior. So, we discussed in our last lecture. Now, we talk about some specific examples of composition related issue or composition related aspect for corrosion protection. And interesting part is it is very difficult to differentiate between composition and microstructure. In fact, both are interlinked. So, we will try to look at the corrosion protection aspects separately, but time to time you will see that there are mixed up, because it is very difficult to distinguish two aspects separately. In fact, if the researchers try to do it. So, if we want to see the composition effect, we fix the microstructure and change the composition, and sometimes we fix the microstructure and change the composition, but it is very difficult. For example, if we consider alloy system, and then if we try to see a simple iron carbon diagram, if we want to fix the microstructure, it is very difficult in the sense by changing the carbon content only, but it will be very difficult because the relative content of the second phase, which is nothing but the cementite, would change, as well as that would lead to a change in the surface appearance of the microstructure, and that would also have effect on the materials corrosion behavior. Fine. So, but we will try to do it as far as possible by giving some examples. So, the course is corrosion protection method. Lecture 14, topic is on materials aspect for corrosion protection. So, if we talk about composition and let us say microstructure, and then finally the influence on surface film or the passivity. Okay. So, if we consider this part only, so then we can cite one example where let us say how this passive film character is changed by because of the change in alloying elements in a 304 stainless steel. Okay. So, here we are not talking about the microstructure part. So, microstructure part we are not talking about here, we are talking about only composition and then its influence on surface film and then its influence on corrosion resistance. And the example, a steel composition is chromium is around 19%, carbon is 0.09%, nickel around 9%, manganese around 0.8 manganese percent, sulfur silicon 1%, phosphorus 0.04, and sulfur 0.03%. So, this is typical composition of 304 stainless steel. So, the stability of the surface film would vary because of change in all those compositions, all those alloying elements. If we note down those alloying element effect individually by seeing the penetration depth, and here the penetration depth, let us say if we talk about effect of chromium. Okay. So, effect of chromium, if you see, okay. So, now and if we talk about penetration per year, millimeter per year. So, here we y axis we are talking about penetration. So, this penetration is equivalent to a corrosion rate, penetration rate, and it can be written in terms of MPY or millimeter per year. MPY is a mils per year, okay. And the convention is nowadays we always mention in terms of millimeter per year. Now, if we talk about chromium content, this is increasing this way. So, now if it is 10%, and here percentage, if remember these are all weight percent. Now, 10, then we have 15, then we have 20, then 25, and this is 1.0, 2.0, then it varies like this. So, you have around 15%, we have around 0.7. So, if we this is 0.7, then 20% we can have it around 17-18%, it will be around 0.3, then around 22%, it will be 0.15 or so, more than 20. So, this is it can be here 3.3%, and around little close to 24%, it could be close to around 0.1%. As a 0.1, sorry. So, these are millimeter per year. So, that means here it is close to around 0.8, this will be close to around 0.4, this will be 0.3, this will be close to 0.1. So, now if we plot it and extend it, extrapolate it, so the plot would look like this. Okay. So, as we decrease the chromium below 15%, suddenly we see that there is a good amount of increase in penetration rate. So, that means good amount of reduction in corrosion resistance. But if we go around close to 18 and more, the improvement in corrosion resistance is not that much, but and that actually gives us an idea that it is not good to go beyond 18-19% in chromium, because it would unnecessarily increase the price of that steel without giving much of effect on the corrosion resistance. So, that is what 304 we maintain chromium percentage around 18 to 19%. So, this is effect of chromium, and when we talk about the effect of chromium, we are actually talking about the stability of surface film. We are not involving microstructure, but microstructure would not change much here, because it will still remain austenite. Okay. So, here we can say that microstructure is almost constant. So, this is austenitic stainless steel, and then we are seeing the effect. Okay. And here the still its solution aligned and quenched. So, when we talk about the processing part, because we have to also involve processing. So, the processing, if we consider in this particular composition case, in all cases those elemental changes are done, and then processing is solution treated, the still sample is solution treated. So, that means it is taken to single phase microstructure, which is austenite, and then quenched. Okay. So, that is the processing route. In fact, here only heat treatment is considered, and that time all the elements are in solution. So, we see the chromium effect. Now, in fact, it would have effect of nickel on it. In fact, we will see that the effect of nickel on the penetration rate will be not that much. Here the nickel content is maintained between a certain range to make it austenite. So, the effect of nickel content would be and remember every time we are considering weight percent of nickel, here weight percent of nickel. So, again this is 1.0, this is 2.0 and millimeter per year, which is penetration depth or penetration rate. In fact, if we do polarization, we will see the equation would be I core or penetration rate would be equal to I core into A, which is atomic number, and then N, which is the number of electron participating for converting 1 mole of metal into its ion, F is 1 Faraday, and rho, which is basically the density of the material. So, I core coming from polarization study is participating for converting one atom to its ion, for example, M n plus Ne equal to M. So, we are talking about N means this one, F is equal to 1 Faraday, rho is density, here it is gram per centimeter cube, and this is, we can get it from polarization study, and if we do polarization study, that time we can get I core. If we do a dissolution study, we just take so this is from polarization study, I core is ampere per centimeter square, okay, it is called amp per centimeter square. Okay. So, this is 96 roughly 96500 coulomb, fine. one can determine this corrosion rate by doing polarization, or this is the route for getting the penetration rate. Somebody can do weight loss measurement. So, that time penetration rate equation would be, so, W divided by A T, W divided by, and W is basically del W, that means the weight loss, A means area, T is time, divided by rho, where all those things are del W is weight loss due to corrosion. A is area, let us say centimeter square, T is time, where it is, let us say second, rho is density, gram per centimeter cube. Okay. So, these two methods one can employ to get to the measurement of penetration rate. Now, if we talk about the effect of nickel on the penetration depth, here, and in fact, we missed one thing. When we talk about this penetration depth, we have to talk about corrosive. We missed that. So, corrosive is here. We talk about corrosive. Here, let us mention corrosive is concentrated HNO3. Okay. So, that is the corrosive. Okay. So, we missed that. So, this is the corrosive. Okay. So, now we are talking about all those penetration depth in that corrosive, and concentration concentrated is around 65% HNO3. If we talk about that, let us say we start from 5%, 5, then 10, then 15, you will see that around close to 8, around 7%, the corrosion rate would be around this level, 8% around this, 10%. So, like this it will vary. Okay. So, if we make a trend line, so you will see the trend line is looking like this. Okay. So, there is not much of variation in the corrosion rate starting from 7 to around 12% nickel. Okay. So, this is effect of nickel. So, effect of nickel, if you consider the corrosion resistance of that material, it does not matter much from 7 to 12% of nickel, but if we get austenite at around 8 to 9%, we should keep it, because otherwise nickel is costly. So, it will increase the cost of the material. Then if we try to look at the effect of carbon, carbon has a serious effect on the corrosion behavior of 304 stainless steel. Okay. So, in that particular concentrated HNO3, in fact, if we change the acid also, it would have similar level of effect. If we talk about effect of carbon, %, 2%, and this is again millimeter per year, and carbon changing from let us say 0.1, 0.2, 0.3 like this. If we see the change close to around 0.03%, the corrosion rate would be very low, 0.03 to 0.02. So, here the value would be 0.02 to 0.03. It's a very low value. Once it goes to around 0.2%, close to that 0.2, the corrosion rate shoots up, and little variation of the corrosion rate would be like this. So, the corrosion rate pattern is like this. So, once it goes close to around 0.3, then the corrosion rate would be very high. Okay. And if we also take a trend line, so the trend line would look like this. Okay. So, this is the trend line you will get. This is the trend line you will get. So, that means it has a severe effect on the corrosion degradation once we increase the carbon content. The only reason could be the this chromium carbide formation along the grain boundary can be a possibility, because once we have extra carbon, the chromium is a strong carbide former, and that can also lead to formation of chromium. It's a sensitization effect can go up. Fine. So, then we can also check about the effect of manganese Okay. So, this manganese effect, if we try to look at, again millimeter per year, 1.0, 2.0, and this was percentage of carbon, this is percentage of manganese. It can vary from 1.0, 2.0, 3.0 like this, and you will see that manganese content, as we have talked about, around 0.8, this will be here, and then around close to this will be here. So, with little extra manganese, we can have a very little down variation in the corrosion rate. Again, the trend line would be almost flat. Okay. So, that means effect of manganese on the corrosion behavior of 304 stainless steel is limited. Okay. And now, if we consider effect of silicon, silicon has its strong effect, at least its effect is more than manganese or nickel. See, if we try to see, extra silicon addition can lead to decrease in the corrosion resistance or increase in the corrosion penetration rate. So, if we consider the effect of silicon, so we are talking about effect of silicon. So, 1.0, 2.0, 3.0 percentage of silicon. So, at a very low silicon content, the corrosion rate will be low, and as we increase silicon, the corrosion rate would also increase, and around close to 20%, it is like this. So, the trend line, again, if we try to draw, trend line would be like this. So, with increase in silicon content in this steel, actually increases the penetration depth, and here penetration depth again millimeter per year. Okay. So, this is effect of silicon and effect of nitrogen. So, nitrogen has its own effect, but it's not that much in this case also. So, nitrogen effect if we consider, so this is effect of silicon, and let us say let us plot effect of nitrogen. Similar plot we can generate. It is 0.1, 0.2, 0.3, and similarly if we have it like this 1.0, 2.0, and this is millimeter per year, and very low nitrogen content. Here also there is not much of variation in the corrosion resistance when we have nitrogen. In fact, we increase in nitrogen lead to increase in corrosion resistance to some extent, and trend line would be like this. Okay. So, this is effect of nitrogen in that particular material. So, the corrosive is 65% HNO3. Microstructure, this microstructure is austenitic stainless steel, and heat treatment is solutionized annealing and then quenching, so that everything is in the solution, and then finally we are getting the variation of corrosion rate in terms of penetration depth per year. And we could see that the effect of chromium is strong, effect of carbon is strong. So, that is what these two elements are very critical. In fact, effect of silicon is also fairly strong compared to nickel and manganese. Now, we could see if we take only about composition fixing the microstructure, we could see that the surface film character is changing with the change in percentage of chromium, nickel, manganese, molybdenum. Sorry, not molybdenum, here no, there is no molybdenum, carbon, nitrogen. So, we have considered 1, 2, 3, 4, 6 elements we have considered. So, that means there is a substantial effect of composition on the passive film character, and accordingly we can have a difference in corrosion performance. So, this is one example of effect of composition, or the when we talk about the material aspects for corrosion protection. That means we have to have good amount of chromium, good amount of very less content of carbon. In fact, if we have 304L, which is low carbon, the carbon content is around 0.02 to 0.03%, we could see that the corrosion resistance improves, because with decrease in carbon content, the corrosion rate reduces to a great extent. We will talk about a few more examples on the passive film character as well as effect of microstructure. In this particular situation, we are only seeing the effect of composition without changing the microstructure. So, this particular example has been taken from ASM handbook volume 13A. This is corrosion resource. Protection, volume 13A. Fine. So, let me stop here. We will consider many such examples which will talk about effect of composition, microstructure processing on the improvement of corrosion resistance of a material. Thank you.